Thank you very much, Honor. Thank you for the invitation. It's really a pleasure to be here. It's my first time at the Arizona State University, although as Honor said, I spent a lot of time in New Mexico between 2000 and 2016. And I really had a great time there. So, and actually, the subject of this colloquium is something that, I started being there in Los Alamos, and, I have been working on this, really for a few years. I find it, quite nice and fascinating, which is this idea of how, skyrmion textures, we'll see what they are soon, or in general, topological solitons can emerge in condensed matter physics, right? So what I will do within this colloquium is first give you a kind of historical perspective of how physicists started thinking about topological solitons, the first topological solitons that appear in the history, and then how that led to some ideas, beautiful ideas that not always worked, but finally these solitons found their place at least in condensed matter physics, and in particular today I will show you how they emerged in quantum magnetism or in magnetic systems. So let me see if this is moving. No. Maybe I should. There is some problem with it. It was working before. So let's see. Like this. Okay. So let's do this. Okay. So so the story starts actually in the 19th century with this man, Hermann Helmholtz. He was a medical doctor and a physicist. And he wrote this paper in 1867, where on the integrals of hydrodynamical equations, which express vortex motion. So he found that certain configurations, called vortices, were very stable. So basically, they were preserved, right, under the time evolution, right. And for those who like, to astronomy, I mean, probably you are familiarized with this great red spot of Jupiter, right? It's actually an example of a vortex, the same kind of vortex that appears in this paper, that has retained its size and shape for at least 300 years. So that gives you an idea of the stability of these patterns, of these vortices. So and another example that probably you have seen in real life is a tornado, right? Which, although it's made of particles of air, right, that are circulating around the core of the tornado, that pattern, right, that vortex pattern is very stable. So it's something that looks like a particle that is emerging in some underlying field, velocity field, of this air. So this idea of Helmholtz inspired Lord Kelvin to propose, right, an answer for the question that they were asking about those days, which was, how, they didn't know what was the structure of atoms. So they were wondering why atoms are so stable, so robust. So the idea that Lord Kelvin had was that actually atoms were vortex lines in ether, right? Remember, ether was the medium where the electromagnetic waves were propagating in those days. And the way he explained the different atoms of a periodic table was through basically assuming that these different atoms will correspond to different types of knots made of these vortices. So this was Lord Kelvin's idea of what was the structure of an atom. Of course, this idea was put out of business at the beginning of the 20th century with Rutherford's experiment, right? Once we understood, that atoms were not really vortices in ether. But, it's a beautiful idea, the idea that particles like atoms can emerge from a more fundamental field, right? And actually, the way of understanding why, let's say, these objects like vortices are so stable, why there is something that is preserved, some pattern, some structure that is preserved, is the following. I mean, maybe with a simple example. I mean, so as I said, In this example of the tornado, you have a field. It's a velocity field of the particles that are moving around the tornado. And we have to remember that the field is actually a mapping between two sets, two manifolds, one that we call the base manifold, the other one is the so-called target manifold. So it's a mapping between two manifolds. And if you want to think of the simplest mapping, we can think of a mapping, let's say, from a circle, from a loop, could be a loop around the tornado, right, into a target manifold that will correspond, for instance, in this example, to another circle. So the target manifold will be a circle, will be an angle, right? The variable. So it's we have a function of an angle, phi, that is a function of the angle tau that basically lives in the base manifold, right? And this angle phi, you could think is simply if we think now of a two-dimensional tornado, right? It determines the direction of this two-dimensional vector, two-dimensional velocity vector. So we have this kind of mapping that, so we have an angle that is a function of another angle. And now what we can ask, right, for this, we can ask the following question. If this variable tau, this angle tau goes from 0 to 2 pi, how many times this angle phi is winding around the circle? And that function is simply given by the integral of d phi d tau times d tau divided by 2 pi. That will give me, because it's the integral of a total derivative, is simply phi at 2 pi minus phi at 0 divided by 2 pi. That must be an integer number. So it's pretty clear that this integral, right, is an integer number. And now the interesting thing is that if I have two functions, phi of tau, that I can deform one mapping continuously into the other one, so I can deform one integrand continuously into the other one, the result of the integral cannot change because the integral is an integer number, and I cannot change an integer number continuously. So that means that if I have two mappings, right, two different mappings, phi 1 of tau and phi 2 of tau, and I can connect them continuously, right, they should have the same winding number. And that tells us that winding number is actually the vortex number. And that tells us that we can classify these mappings, right, in different, according to this winding number that defines what is so-called homotopy classes, right? So basically, mappings or configurations that have the same winding number, they are in the same homotopy class. And these homotopy classes form a group. We can compose these mappings in some way. And then there is a group structure, right? So for instance, if you start with two vortices, with vorticity 1, you compose them in some way, you can get a mapping with vorticity 2, right? So there is also something called homotopy group associated with these homotopy classes, right? But the important thing to remember is that, we have this winding number, this topological degree that is characterized in these mappings. And because the time evolution of my field, right, now imagine that we have time, we solve an equation of motion, corresponds to some continuous evolution of my mapping, this number will be preserved. Because I told you that if I deform continuously, right, a mapping, there is a number that is conserved. In the same way that the charge is conserved, this winding number will be conserved. And that is what gives stability to these configurations, right? The fact that if I deform them continuously, there is something that is being conserved, it's not changing. And if you think about the time evolution of one of these mappings, right, the winding number in this case will be conserved. So it works like a conserved charge, right? But it's topological. Good. So elaborating on this idea, this man, Tony Scam, who was a British scientist that was actually part of the Manhattan Project. So he was here, not far from here in New Mexico in the 40s. And in the 60s, he had this idea that actually baryons, right, neutrons and protons in the atom, could be topological solitons, right, of some underlying more fundamental field, the pions, right? And in that case, these baryons, or these so-called skyrmions, we call them skyrmions because of him, correspond to the classification, the homotopic classification of mappings from the full ball. Now it's no longer a circle, it's a ball. That ball represents the three-dimensional space. We'll see how we can compactify a three-dimensional space into a ball, into another ball that corresponds to SU2 rotation. So the field in his case, was not a vector field or my angle. It was an SU2 rotation, SU2 rotation matrix, right? And he wrote an action where he obtained, solitons, skyrmions, sorry, from this action. And he proposed that, these baryons, neutrons and protons, were actually topological solitons of some more fundamental field. That is in the 60s. Of course, later on, chromodynamics, came with an alternative story and prevailed. Although, if you take the Larsen limit of chromodynamics and you apply a dual transformation, that's something that we can do. You can connect actually chromodynamics with his story, right? So this idea that baryons are topological solitons of a more fundamental field is not completely crazy. Actually, some physicists in Oxford, they are still working with this action and trying to reproduce the periodic table, right? They're getting heavier and heavier nuclei, right? Of course, the number of skyrmions will be the number of nucleons, right? And playing with this. Anyway, something that you may wonder is, what were the hidden influences, pushing SCIM towards this kind of picture, of soliton picture, right? This idea that nucleons could be topological solitons of a more fundamental field. And it turns out that, SCIM's interest in Kelvin, right? He knew about Kelvin's work, right? He knew the story that I just told you. And his interest in Kelvin was sparked at an early age by the presence of this tight predicting machine that was constructed by his great-grandfather, right? The machine was conceived by Kelvin, right? And his grandfather built it, and this guy grew up in the same house, so he learned, about these ideas, and he was a big fan of Kelvin. So he thought that maybe the idea that didn't work for atoms could work for nucleons. Now, the story that I want to tell you today is that although, okay, none of those ideas worked for the target that they had in mind, skyrmions, found their place in nature, but instead of appearing in the context for which they were proposed, at least, the story I want to tell you today is how they emerge in magnets. And magnets are basically solid state, so materials where, as you know, you have atoms. In the atoms, you have electrons. The electrons are orbiting around their atoms. That produces some orbital magnetic moment, and in addition, they carry a spin. So because of that, they have a net magnetic moment, right? And those magnetic moments can arrange, they give rise to a field, again, to a vector field, the spin field. And those magnets, those moments can arrange in different ways. They can form ferromagnets, antiferromagnets, and as we will see today, skyrmion textures. So the first thing, I want to clarify, this slide is only not to confuse you, is the spin is a quantum mechanical object, but all these theories for topological solitons are built after taking a classical limit, right? So what we are going to do is we are going to start, with usual quantum mechanical spins. They are operators, as you saw in your class of quantum mechanics, but we are going to take the classical limit. Strictly speaking, that classical limit becomes exact when the size of the spin goes to infinity, right? That is never true, but it becomes a good approximation when the spin is large enough. And then you can represent the spin operator with the expectation value of the spin in a so-called spin coherent state, right? And your quantum mechanical spin becomes kind of a classical vector that has a finite norm. So my target manifold now is the surface of a sphere, right? The spin can point, my classical spin, if you want, is a vector that can point in any direction of the sphere. And the equation of motion, the Heisenberg equation of motion for the spin operator, in the classical limit becomes the so-called Landau-Lifshitz equation of motion that probably many of you are familiarized with. So which is this equation, right? And it allows you to, given some initial configuration of the spins, compute how they will evolve in time. Okay, so one can solving these equations, one for each spin, one can use the computer, for instance, and get the time evolution of a spin configuration. Good. So Now, how the skyrmions appear in the picture? Well, what I'm going to do is consider what are so-called baby skyrmions in high energy. We call them skyrmions in condensed matter physics because they are the most common ones. And the important thing is I'm going to consider for a moment that I have a two-dimensional system like a film, right? That is going to be my base manifold, a plane, an infinite plane. And then, as I said, my target manifold will be a spin, right, that lives on the surface of a sphere, right? But I'm going to add a condition. I will consider only spin configurations that are constant at infinity. No matter in which direction I move, they go to a constant value. Which means that now I can identify any point at infinity with a single point. That is called compactification of the plane, right? I add another point to the plane that is infinity, and I associate, to that point any point that is at an infinite distance from the origin, right? And if we do that, if we associate any point that is infinitely far away from the origin with a single point, then we can compactify the plane, meaning that we can establish a one-to-one mapping between points on the plane and points on the sphere. And you can see here how the mapping works. So if I have, let's say, a point on the plane, I can send a line, a straight line from the North Pole to this point, and that straight line will intersect the surface of the sphere at a given point P1, so I have a one-to-one mapping between these 2 points. Of course, as this point moves to infinity in any direction, from any direction will reach the North Pole. So the North Pole corresponds to any point which is infinitely far away from the origin, all right? So for instance, if I have a configuration, a spin configuration like this one, where the spin is pointing down at the origin and up very far away, when I do this mapping of the plane to the sphere, my spins end up on this, after the stereographic projection of the plane to the sphere, my spins end up looking like this, right? At the South Pole that corresponds to the origin, they are pointing down. At the North Pole that corresponds to any point far away from very far away from the origin, they are pointing up, right? And now it turns out that for these mappings, you see, we replace a mapping from the plane to the sphere into a mapping from the sphere to the sphere, because I converted the plane into a sphere. So now my base manifold is a sphere, my target manifold is a sphere. I have a mapping from the sphere to the sphere. And it turns out that in the same way, for mappings from the circle to the circle, I could count the winding number. Remember the number of times this mapping is winding around the circle. Here, what we can count is how many times this mapping is wrapping the sphere, right? So not wrapping the circle, wrapping the sphere. And for that, all we need to do is we have to compute the solid angle, right, spanned by these 3 spins, right, or the density of solid angle, which turns out to be this quantity. Is, again, the solid angle spanned by these 3 spins, and then integrate that solid angle over the full plane, right? That's what this integral is doing. This is the density of solid angle. You integrate over the full plane. You compute the solid angle spanned by this spin field. You divide by 4 pi, that is the solid angle of the sphere, and you count how many times my mapping is wrapping the sphere. So that is called skyrmion number, right? Unlike the vortex number, it's a topological invariant, right? That tells me how many skyrmions do I have in my configuration. For instance, in this example, right, it is clear that the spins are wrapping the sphere only once, right? The solid angle, spanned by the spins when you integrate it over the full sphere will be, you will get 4 pi. So you divide by 4 pi, you get 1, right? And the other interesting thing is, like, as I told you before, if you deform this mapping continuously, for instance, if you rotate all the spins continuously about the z-axis, you will get another configuration that still has skyrmion number equal to 1, because remember that this number, this topological number, doesn't change when you deform the mapping continuously. This will be an example of a continuous deform. I mean, I can go continuously from this mapping to this one, and I will get the same skyrmion number, right? These are called Néel skyrmions. These are called Bloch skyrmions. But in both cases, I have only one skyrmion. Okay, so this is all very nice, but until 2009, we didn't know that it was possible to find these spin configurations in equilibrium that will have a finite Skyrmion number, right? And in 2009, a German group did this neutron scattering experiment on manganese silicide, where they saw that basically they measure a phase diagram like this one. This is magnetic field in the vertical axis. This is temperature in the horizontal axis. And what they saw is that at very low temperatures, they saw a helical ordering. In a neutron scattering experiment, a helical ordering manifests via Bragg peaks, let's say for some pair of wave vectors, only two of these circles if you want. But what they saw is that if you increase the magnetic field and increase the temperature, now suddenly, instead of seeing only two peaks, you see six. You hear a hexagon, which, if you want, corresponds to a superposition of spirals like this one, running in three directions with propagation vectors that differ by 120-degree rotation. Right? So basically, you have a superposition of three spirals that leads to this kind of Skyrmion crystal. And of course, in 3D, like the vortices, the Skyrmions become lines, right? So you have these columns or these Skyrmion lines that are forming a hexagonal lattice. So they found in this phase a hexagonal Skyrmion crystal. Very good. So this was quite surprising, right, for the whole community. Some people didn't believe, because sometimes it's difficult to distinguish this structure from domains, three different domains of this spiral ordering. But 1 year later, let me skip this. 1 year later, a Japanese group managed to observe these Skyrmions with real space visualization techniques using Lorentz transmission microscopy. They were able to observe the Skyrmion crystals in films, right? So they send electrons, they do the techniques is called Lorentz transmission microscopy. They send electrons, and then the electrons are deflected by the local magnetic moment, right? Produced by the spin. And with that, they can reconstruct these images. And you can see here, for instance, if the spiral ordering, the helical ordering, this is what happens in the Skyrmion phase. And something nice is that when you make films instead of bulk materials, the Skyrmion phase becomes more stable. Now it remains stable down to zero, the zero temperature, right? So you see a transition from, if you increase the magnetic field, that is what is happening here, you see a transition from the helical ordering to the Skyrmion crystal. And eventually, if you keep increasing the magnetic field, you fully polarize the spins, and you get a forced ferromagnetic state. But even in this region, right, in this ferromagnetic region that is forced, is induced by the magnetic field, you can create, this, one can show that a single Skyrmion is a metastable state. So if you create a Skyrmion, it will live for a very long time, right? So if the temperature is low, you can create a Skyrmion and then move it around, right? And it will behave as an emergent particle, as a mesoscale particle. So that's nice, because one can send information, right? With those mesoscale particles. And actually, there are by now many experiments that show basically these Skyrmions. Let me see if, no, sorry. So this slide is showing, Skyrmions in the creep regime. So basically, you can drive the Skyrmions by applying an external current, spin polarized current. So once you form a Skyrmion, you can move it by applying a current. And the mechanism that you exploit is something called spin transfer torque, right? So you can create this, each of these is a Skyrmion. As you can see here, they behave as particles. And here they are in a creep motion regime, because there are pinning centers that tend to pin the Skyrmions. And the current, this current that you are applying to drive the Skyrmions is still very low, right? To go to another regime where these pinning centers will become irrelevant. So you are in this kind of creep regime. But the whole purpose of this slide is to show you that these skyrmions really behave as particles. They conserve this skyrmion number as they move, right? So you have mesoscale particles that you can use to send information. And in principle, there are some ideas for replacing or for using this property for magnetic memories, right? However, today I'm not going to focus on that aspect of the skyrmions. Skyrmions are interesting not only because they behave as particles and you can store information or move information from one place to another. Skyrmions are also interesting because they have a very, I would say, unusual effect on conduction electrons, right? So imagine now that you have local moments. So let's say some of our electrons, so let's say you have some material with transition metals, these are these elements here. So that means that the valence electrons occupy the orbitals. And then that because of some crystal field splitting, right? Remember, we have 5d orbitals from atomic physics. Let's say that they split into a triplet. This is called T2G triplet, and a doublet, EG. And again, from atomic physics, remember the Hund's rules tell us that if you have, for instance, 4 electrons in these 5 orbitals, you want them to be all ferromagnetically aligned, right? But here, you have these 3 low energy levels where you occupy each level, and here you occupy this one. But for instance, you can have another ion where here this orbital is empty, but these 3 are occupied, right? So you have a situation where you have between 3 and 4 d electrons in the valence orbital. Then clearly these ones will remain localized because the Pauli exclusion principle tells me that I cannot go and double occupy this one if it is ferro. And then this other electron that can itinerate, that will make the material a metal because this electron can itinerate, has a very strong ferromagnetic interaction with the local moments, right? So the question that I want to pose is, what happens if these local moments are forming a skyrmion texture? What is the effect of that skyrmion texture on these conduction electrons, right? And as we will see in a moment, that effect can be extremely strong, right? And actually, it's pretty interesting, the kind of field that these skyrmions induce on the conduction electrons. As I said before, one way of thinking of this skyrmion crystal is as a superposition of 3 spirals that are running in 3 directions that differ by 120 degrees, right? So keep in mind that we can think if we Fourier transform this spin texture, you will see peaks at wave vectors that differ by 120 degrees. So in some sense, this skyrmion crystal is like a superposition of 3 spirals. Okay, so to understand the effect that the skyrmions will have on conduction electrons, it is important to remember a bit of quantum dynamics, quantum mechanics. Remember, if you have an electron in a magnetic field, let's say represented by this vector potential here, and we move the electron around the flux of that magnetic field, the wave function of the electron will pick up a phase, right? That phase is called a Aharonov-Bohm phase or a Aharonov-Bohm effect. Now, when you do the same on a lattice, right? When normally in solid-state physics we work on a lattice because we have a periodic array of atoms, and then we only consider, let's say, 1 orbital per side, right? So this minimal coupling, this way in which the magnetic field enters in the Hamiltonian of an electron, now becomes simply a phase in the tunneling or hopping matrix element that corresponding to the electron being able to move from this atom to this atom, right? So in a solid, you have some finite tunneling matrix element for an electron to move from, let's say, 1 atom to another one. And the effect of adding a magnetic field is that this tunneling matrix element now acquires a phase. And it turns out that once again, the circulation of this phase, the sum of the phase theta 1, 2 plus theta 2, 3 plus theta 3, 1, turns out to be equal to the flux, right? enclosed, 2 pi, actually there is a missing 2 pi, times the flux divided by phi naught, right? So essentially, this is the way this bomb Aharonov effect manifests on the lattice. So very similar to the continuum, right? The hopping matrix element or the tunneling matrix element acquires a phase, and the circulation of the phase is determined by the flux enclosed by the loop. Okay, so now what we can think is, what I want you to see is what is the effect, let's say, of an underlying spin configuration, right, on conduction electrons. Let's say we have this term that represents the kinetic energy of my conduction electrons, is so-called tie bonding term in solid-state physics. And then this term that represents the Hund's coupling, if you want, that tends to align the spin of my conduction electron, that is the blue guy here, with the spin, the classical spin that represents the localized spin degree of freedom. So what happens is that when this, if we are in the limit where this exchange is much bigger than T, right, this spin is forced to be parallel to N1. So when it hops, when it moves to the neighbor, right, of course, it will end up in a situation where the spin is not aligned with N2. So what happens is, because we have this condition at low energies that, we have to project, basically, first order perturbation theory tells us that we have to project this state into the low energy state that corresponds to aligning this with this. So our effective tunneling now turns out to be proportional to the inner product between N1 and N2, right? So basically the coherent state associated with this spin orientation and the coherent state associated with this other spin orientation. And it turns out that this inner product gives you a phase, right? So the effective tunneling of this conduction electron in the presence of these local magnetic moments that are not collinear gives a phase to the hopping, to the tunneling. And geometrically, that phase is simply half of the solid angle spanned by the spins N1 and N2, and then some reference vector that I can choose as I like. Of course, depending on the reference vector, I will get a different solid angle. So that's not, we say it's not a gauge invariant. But the phase associated with the hopping of my electron from here to here, if I force the spin of the electron to be parallel to the orange spin, is given by simply half of the solid angle spanned by these 3 vectors. Of course, if you now ask what is the phase here, it will be the solid angle spanned by these 3 vectors. And finally, for the last phase, it will be the solid angle spanned by this one, and this one. So the sum of the 3 solid angles, right, the sum of this phase, the phase associated to this inner product, plus this one, or in other words, the circulation of the phase, is a geometric invariant that is the solid angle spanned by the 3 underlying local moments, right? So I add, once again, this phase plus this phase plus this phase. This is what I'm writing here. That is half of the solid angle spanned by the 3 spins. And now, right, you can see that I cannot distinguish that phase, that geometric phase is called Berry phase, from the Bohm-Aharonov phase that the same electron will pick up if there were a coil, right, inside this loop. If I had an actual magnetic field, right, acting on my electrons, I will also get a phase, I told you, right, 2 pi phi naught, phi over phi naught, right, which I cannot distinguish from this other phase that the same electron will pick up in the presence of this non-coplanar spin configuration. So what this is telling us is that a non-coplanar spin configuration generates a synthetic and effective magnetic field that is whose, remember, the density of flux is magnetic field. The density of solid angle is this quantity, is the Skyrmion density. Remember, I told you, the Skyrmion number is the number of times, right? My mapping is wrapping the sphere, so it's the integral of the angle of the density of solid angle. Well, there is an effective magnetic field that is proportional to the Skyrmion density or the density of solid angle, right? So in other words, what we are saying is if we have a Skyrmion, right, the electron will feel an effective magnetic field, and basically, remember, the Skyrmion covers the full sphere, right? So the solid angle spanned by the whole skyrmion is basically 4 pi, right? 4 pi divided by 2 is 2 pi. That means that one skyrmion corresponds to one flux quantum. The effective field produced by one skyrmion is one flux quantum. Moreover, if you now allow the spins to change in time, you will have also an emergent electric field. So what that means is that these spin textures, right, like skyrmions, can produce an electromagnetic field, if you move them in time, that couples to the conduction electrons. Right? And now you can play games with this because, of course, if you have a synthetic magnetic field, then you could have, for instance, a Hall effect, right, induced by the skyrmions. Now, what makes the whole observation, like Hall effect, for those, I mean, probably you all know, I mean, but essentially means that, if you apply, remember, if you inject some current, right, in the presence of a magnetic field perpendicular to your film, that will induce a transverse voltage that turns out to be proportional to the magnetic field, right? This was discovered in 1879 by Hall. 1 year later, he noticed also that in ferromagnets, there is an extra contribution that is proportional to the magnetization, not just the field. This was called anomalous Hall effect. But now what I'm telling you is something else. There is an extra contribution, topological contribution, we call it sometimes, that comes from a non-coplanar spin configuration like a skyrmion that will also contribute to this Hall resistivity, right? So this is new. As you will see later in the talk, you can have this topological contribution even without a net magnetization. Yes? Of which magnetic field? The effective magnetic field? Yes. Yes. Yes, it is. Yes. And the other important thing is that it couples to the electrons only to the orbitally, right? So a real magnetic field couples to the spin and to the orbital, right? Degrees of freedom of the electron. This is only orbital coupling, right? So this is an effective magnetic field only from the point of view of the orbital coupling, not from the point of view of the spin coupling, right? Good. Okay, so what we can understand here also is that, okay, if we go back to this material manganese silicide where they reported the first skyrmions, and you ask, what is the size of the skyrmions? Well, typically, in these materials is 10 nanometers. That means that you have a flux quantum in an area of 10 nanometers squared. If you put numbers, right, so you say, well, I have one flux quantum in 10 nanometers, what is the effective magnetic field associated with that? That is 100 Tesla. For those who are not familiarized with units of magnetic field, to reach 100 Tesla, you need to go to Los Alamos to the High Magnetic Field Laboratory, and it's only with pulse fields that you can reach 100 Tesla. 100 Tesla is a huge magnetic field, right? If you want to apply an external field to produce the same orbital effect. So that shows that in principle, you can produce a huge orbital effect or Hall effect just by inducing this spin configuration. So how is that people like Onur or me or condensed matter or Antia can help here? Well, one thing we try to understand is how to find these skyrmion crystals that can produce such a huge anomalous Hall effect in real materials. What is the recipe, right? Or the design principles, we call it in proposals, to find these kind of states. And that is, what I will try to explain during the rest of the talk. And the first ingredient, if we are thinking of a recipe, is a spiral, right? I told you I can think of a skyrmion as a skyrmion crystal, to be more specific, as a superposition of 3 spirals. So the first question you may want to ask is how can we find spirals in nature, right? Spiral orderings in nature. Well, the answer for manganese silicide and these so-called B20 materials is that it comes simply from the competition between 2 interactions. One is a Heisenberg interaction, this kind, S.S. This was proposed by Heisenberg in 1828 to explain ferromagnetism. And this so-called Zheroshinsky-Moria interaction that actually is about 50s and 60s. This is Igor Zheroshinsky. He proposed interaction on phenomenological grounds in Russia. This is Toru Moria, by the way. It's very difficult to find a picture of this man. he also wrote a nice paper in the 60s. This type of interaction you see is S cross S. It appears because of the combination of the spin-orbit interaction that we learned in quantum mechanics and the crystal field, right? In a crystal, the neighbors of an atom form a field that is not spherically invariant, and the combination of those two leads to these kind of anisotropic interactions, right? This one is not invariant under a rotation of the two spins. This one is, right? So these interactions appear. And what you can see here is that this one, if this J is positive, so that we have a negative, we like the spins to be parallel, ferromagnetically aligned. But this one is S cross S, will be unhappy because S cross S is 0 if the spins are parallel. So the best trade-off corresponds to a spiral, right? One can demonstrate. And what determines the width, the wavelength of the spiral is the ratio between D and J, right? That's the best trade-off between the two interactions. And actually, in manganese silicide, the size of the skyrmions is determined precisely by this ratio. Those 10 nanometers come from the fact that, roughly D is 10 times smaller than J, right? So this is the wave vector. Remember, the wavelength is 2 pi over the wave vector. Good. That's not the only way of producing spirals. The other way of producing spirals is to have a competition between ferromagnetic and anti-ferromagnetic. So let's say you have a nearest neighbor ferromagnetic interaction and a second neighbor anti-ferromagnetic interaction. Once again, if the anti-ferromagnetic interaction is bigger than a critical value, I can always write my spin Hamiltonian in momentum space, and then finding the optimal spiral simply means minimizing this function J of k, that in this case is the sum of these two cosines, cosine of k coming from the nearest neighbor interaction, cosine of 2k from the second neighbor. And then when you minimize, you get that, okay, for a while, if J2 is very small, you get the minimum at q equals 0, but eventually you start splitting, right? The system, you start having two minima at q and minus q when J2 is bigger than a critical value. And this transition from q equals 0 to 2 minima is called Lifshitz transition because of this man, Evgeny Lifshitz, that was, I think, the brother of the Lifshitz of the equation of motion of the spins. Good. So that's another way, competition between Shaloshensky-Moria and ferromagnetic interaction, or competition between a ferro and an anti-ferromagnetic interaction that can lead to spirals. And this is all in 1D, but if you go to now a two-dimensional system, remember I told you to get skyrmions, we need a film, or we need at least 2 dimensions, then we can again play the same game, a triangular lattice, nearest neighbor ferromagnetic, interaction, second neighbor, or third neighbor in this case, anti-ferromagnetic, it doesn't really matter. You go to momentum space, and now you find the same story. If this J3 is very small, J1 is negative, you get a ferromagnet, but then above a critical value of J3, you start seeing 6 minima, right? Correspond to plus minus Q1, Q2, and Q3, right? That correspond to the points, the vertices of a hexagon. So, it's simply minimizing this function that is 6-fold symmetric because the Hamiltonian, the system, is 6-fold symmetric. And something that is really important here is that Q1 plus Q2 plus Q3 is equal to 0, right? Because they are vectors that differ by 120-degree rotations, right? I will not enter in details of why it is important, but it has to do with the fact that, the second, if you have a superposition of spirals, you generate harmonics, right? So if you superimpose a spiral with Q1 and Q2, one spiral with Q1, one spiral with Q2, you generate a harmonic at Q1 plus Q2, right? That in this case turns out to be minus Q3, that is also a minimum, right? So somehow you don't pay energy for the first harmonic. And that is only true when you have a hexagonal system. If you had a tetragonal system, you had only Q1 and Q2 that differ by 90 degrees, then Q1 plus Q2 will not be a wave vector that minimizes this function, right? So it's important here that you have a 6-fold symmetric system. You will see in the final recipe if I had to talk to someone making materials, I will tell them, if you're looking for skyrmions, look for materials that are six-fold symmetric, right? That are hexagonal. Okay, and when you go and minimize the energy, right, you can use Monte Carlo techniques. These are classical spins. This is precisely for the model that I just described. And then indeed, they get, as expected, they get a spiral with this a wave vector that depends on the ratio J3 over J1. But with temperature, they can induce a skyrmion phase, right? So essentially, that model that I just described has the triple Q, the skyrmion crystal, but again, like in the case of manganese silicide, induced by magnetic field and induced by temperature. However, if you add a small easy axis anisotropy, so if you introduce a term in the Hamiltonian that favors one spin orientation, right, breaks the rotational symmetry, then it is possible to get skyrmions, a large skyrmion phase, basically even at zero temperature, right? In this phase diagram at zero temperature, there is no skyrmion phase. The skyrmion phase is thermally induced. But in this phase diagram, where this is the easy axis anisotropy and this is the magnetic field, you get a pretty big skyrmion crystal phase induced by magnetic field, always induced by magnetic field, but you need the anisotropy, the easy axis anisotropy, to get the phase at zero temperature. And something that is quite nice is that if you take the long wavelength limit, so if you take the limit where the wavelength of these spirals or skyrmions is much, much bigger than the lattice space, you can write now Hamiltonian in the continuum. And actually, the phase diagram in the continuum, now the 6 minima that you had for the lattice become basically like instead of a hexagonal shape, we have a Mexican hat. So now any wave vector on this ring will minimize the exchange interaction. But still, the phase diagram is basically the same phase diagram that I showed you before. This is magnetic field, this is easy axis anisotropy. So we say that the phase diagram is universal because you can get rid of the lattice and you still get this skyrmion phase induced by field in the presence of some easy axis anisotropy. And a way, if you want to understand this intuitively, right, the way you can think of this is, remember, at low fields, we have a spiral ordering. That means that the spiral, of course, sometimes is pointing along the field direction, sometimes is pointing in the opposite direction. And now the way the system, if you apply, let's say, red here corresponds to the spins parallel to the field, blue to the spin anti-parallel to the field, and these white lines correspond to these regions where the spin is twisting, right, fast to go from up to down, right, to parallel to the field to anti-parallel. And in general, what you can see is that the energy gets accumulated here. So these are like lines with a finite tension, right? Okay, so what you would like to minimize the energy is to minimize the density of these lines, right? Of course, if you keep, what the system does at the beginning, it forms the spiral, so you have a bigger region, a bigger blue region, right? And a bigger red region and a smaller blue region, right? So what the system, the way the spiral can distort to satisfy the Zeeman term, the presence of the magnetic field, is by increasing the width of the red region at the expense of decreasing the width of the blue region. But the density of these white lines is not changing, right? However, if I have a superposition of 3 spirals, I will have a pattern like this one, right? So this will be the skyrmion crystal. And now you can see that as I increase if I increase the field, I increase the area occupied by the red region. Of course, the perimeter of this white region around the core is shrinking, right? It's getting smaller. So it's a very simple geometric calculation to find out, what is the magnetization value, right? For which it becomes more convenient. You have less perimeter of these lines per unit of area in this case than in this case. And that turns out to happen more or less at 1/4 of the saturation value of the magnetization when all the spins are parallel. And that is pretty much where you see the transition from the spiral ordering to the skyrmion crystal. So somehow that gives you a kind of intuitive way of understanding why the combination, and here is important, sorry, the combination of an easy axis anisotropy, right, and a magnetic field, right, that tend to polarize the spins along one direction, right, and then fast, change to the other direction, leads to this skyrmion crystal. So you need both things, the magnetic field and the easy axis anisotropy. So to basically show you how now find these, other examples of skyrmion crystals in nature, you can simply consider now these rare earth elements, right? What is special about these rare earths, the so-called lanthanides, is that it's very easy to find the situation where you have localized magnetic moments now in 4 f orbitals that interact with each other via conduction electrons. So now 2 moments interact with each other via conduction electrons. And one example will be this gadolinium-based material. So here you see gadolinium is one of these rare earths. And if you consider materials, like this one, right, made of gadolinium, look at this is a hexagonal material, it has gadolinium. There is a localized magnetic moment, more or less, of 8 Bohr magnetons. It corresponds to a 4f7 configuration. And the idea is that, as I will mention in a moment, these moments interact with each other via the conduction electrons that are moving on top of them. So in this material, this is from 2019, a Japanese group made and measured basically the Hall resistivity as a function of magnetic field, and they saw something like this. So at low fields, they see a normal Hall effect, right? They see a Hall resistivity proportional to the magnetic field. But then when they enter in this phase, in this intermediate phase, you see this huge change of the Hall resistivity. So this is an example of this topological Hall effect, right, where the Hall resistivity is induced by a skyrmion crystal, right? Actually, when they did other experiments like neutron scattering and X-ray diffraction, they saw that indeed there is a skyrmion crystal here. So this is an example of how the skyrmion crystal and the huge effective field produced by the skyrmion can produce a huge effect on a transport property like the Hall resistivity. And what I was trying to say is that in the way you understand the origin of the spirals here is that the spins interact via conduction electrons. So the idea is that one spin will interact with the spin of conduction electrons that will produce Friedel oscillations. And then the other spin will notice those oscillations. And then effectively you'll have an interaction where you naturally get a minimum at a wave vector that is roughly 2 times the Fermi wave vector. So a wave vector that connects 2 points on the Fermi surface. So that gives a natural way of producing spirals. Actually, in this material, you can see that this is the Fermi surface of this material. And you can see that indeed there is the ordering wave vector is a wave vector that is connecting parallel regions of the Fermi surface. So there is nesting. And just to close, right? Let me mention something funny. I mean, 2008, 1 year before the discovery of the skyrmions with Ivar Martin in Los Alamos, considering the same kind of model, right? Conduction electrons now instead of Hunds is a Kondo coupling, exchange interaction. But on the triangular lattice at this particular filling fraction, you get a Fermi surface like this one, a regular hexagon, that has nesting at these 3 wave vectors that are half of reciprocal lattice vectors. And it turns out that the superposition of 3 spirals, in this case, where you have a large wave vector, not a small wave vector, is a four sublattice structure like this one. So, it's a triangular lattice. You get a four sublattice structure where the spins at each of the 4 sublattices are pointing along the all-out directions of a regular tetrahedron. What that means, if you think about it, is that the solid angle spanned by the 3 spins on one triangle is a quarter of the solid angle of the sphere. That means that you have a quarter of a flux quantum on every single triangle. And it's always the same, right? So you get exactly the same situation on every single triangle. You have a quarter of a flux quantum. So in some sense, this fictitious magnetic field now is uniform, completely uniform. And actually, if you think about it, this is like the short wavelength limit of a skyrmion crystal. If you were pushing all the skyrmions together, you will end up with something like this, where every 4 triangles you have a flux quantum. So if you want, of course, this is pushing the limits because the idea of skyrmions is always well defined in the long wavelength limit, but this is like the short wavelength version of a skyrmion crystal. And indeed, when you solve the electronic problem in the presence of these skyrmions, of this forced lattice structure, you get something called integer Hall effect. So not only you get a topological Hall effect, the system becomes an insulator, and then the whole conductivity is quantized, right? So the interest in this kind of state of matter is called Chern insulator, is that you can have dissipationless currents, the boundary, right, through basically an insulator that is basically emerging from a spontaneous symmetry breaking, right? So you can use the spins to induce, a Chern insulator below the ordering temperature of the system. And the nice thing is this magnetic ordering was found this year, right, in a material. Unfortunately, it doesn't fully gap out the Fermi surface, but there is indeed an anomalous Hall effect that the topological Hall effect can also be measured in this method. So the list of materials that they are finding nowadays, it keeps increasing. I would say to close that, based on what we learned, and this is the kind of information that we give to experimentalists, is what are the ingredients if you want to find skyrmions in nature. First, you want hexagonal magnets for the reason that I mentioned before. You want hexagonal magnets that have long wavelength in plane spirals. In the hexagonal planes, you want to have some spiral ordering at zero field. And then you would like to have a small easy axis anisotropy. And then the recipe will be hook the magnet, apply magnetic field, measure the field dependence of the Hall effect, like it was done for this gadolinium material. And then if you want to confirm that you have this skyrmion crystal, either do Lorentz transmission microscopy if it is a film, or do neutron scattering or X-ray diffraction if it is a bulk material. So to conclude, right, we have seen that metastable single skyrmions and stable skyrmion crystals can emerge in quantum magnets, right? Skyrmion crystals can produce an astronomically large effective magnetic field, so we can use that to control the transport properties of conduction electrons that basically are orbitally coupled to these skyrmion crystals via this effective magnetic field. And then, as I mentioned, this synthetic magnetic field can be very large. So you can imagine situations where you have, for instance, a topological a quantum Hall insulator even at ambient temperature, right? One of the dreams is to say, well, if you have some magnetic ordering happening at ambient temperature that fully gaps out the Fermi surface, then you could have a Chern insulator at high temperatures, as I said, that will have dissipationless currents on the boundary. So it's a way of generating dissipationless currents at pretty high temperatures. So thank you very much for your attention.